How long would it take to reach Jupiter? It seems like such a simple question, a straightforward measurement across the solar system. Yet the answer is not a number. It is a constellation of possibilities, each shaped by physics, orbital geometry, and the precise moment we choose to leave Earth. Some missions have arrived in just over a year, others have taken nearly 6. The same destination, wildly different journeys. Tonight, we will unravel this mystery together, tracing the invisible pathways that connect our world to the giant of our solar system, Jupiter. Even the name carries weight. The king of planets, a world so immense that 1,300 Earths could fit within its volume. Its great red spot alone, a storm larger than our entire planet, has raged for centuries, perhaps millennia. Bands of ammonia clouds swirl in ochre, cream and rust, driven by winds that reach speeds of 400 miles per hour. 4 major moons, the Galilean satellites, orbit like a miniature solar system, each one a world unto itself. Europa with its hidden ocean, Io with its volcanic fury, Ganymede larger than Mercury, Callisto ancient and cratered beyond measure. To stand in Jupiter's presence would be to witness creation itself, a celestial forge where hydrogen and helium churn beneath crushing gravity, where auroras dance across magnetic fields 1,000,000 times stronger than Earth's, where time and scale dissolve into something beyond human comprehension. But reaching Jupiter is not simply a matter of pointing a spacecraft outward and waiting. Between us and that magnificent world lies a labyrinth of variables that transform a simple question into an elegant puzzle. Light itself, travelling at its cosmic speed limit, takes between 33 and 52 minutes to cross the gap, depending on where Earth and Jupiter stand in their eternal dance around the Sun. Yet we are not made of light. Our spacecraft are bound by chemical propulsion, by fuel mass, by trajectories that must account for orbital velocities measured in kilometers per second. We cannot travel in straight lines through the vacuum. We must fall along gravitational curves, timing our departure to windows that open only once every 13 months, riding orbital mechanics like sailors reading celestial winds. The answers we will uncover tonight are not what you expect. We will journey through the actual missions, Voyager's breakneck sprint past Jupiter in just 546 days, Galileo's leisurely 6-year voyage that used Venus and Earth itself as gravitational stepping stones, Juno's precise arrival after nearly 5 years of flight. Each mission chose a different path, a different philosophy, trading speed for fuel efficiency, directness for gravitational assists. We will explore theoretical propulsion systems, ion drives, nuclear rockets, even technologies that exist only in blueprints and equations that could one day cut the journey to mere months. And we will face the most sobering question of all. What would it take to send humans, not just machines, across 400 million miles of radiation-soaked void? This is not a journey measured only in time. It is measured in patience, ingenuity, and the delicate mathematics that govern how worlds move through space. Tonight, you will understand why the question, how long to Jupiter, has no single answer, only a spectrum of possibilities, each more fascinating than the last. Before we drift further into the cosmic depths, I'd like to know, where in the world are you watching from right now? What time is it where you are? Drop a comment below. There's something beautiful about knowing we're all scattered across this planet, looking up at the same stars, wondering about the same questions, together in curiosity, even as we're apart in space and time. Now, let us begin. Let us trace the invisible roads between worlds and discover what it truly means to travel not through space, but through the architecture of gravity itself. Before we ever leave Earth's atmosphere, before we calculate trajectories or design spacecraft, we must confront a profound and elegant truth. Jupiter is never in the same place twice. Neither are we. The distance between Earth and Jupiter is not a fixed number. It is not a line drawn across the void. It is a relationship, constantly shifting, constantly evolving, dictated by the ancient rhythms of orbits that have been dancing around the Sun for billions of years. To understand how long it takes to reach Jupiter, we must first understand that distance in space is not measured like distance on Earth. We cannot simply point at Jupiter and draw a straight line. The cosmos does not work that way. Both Earth and Jupiter are in constant motion, circling the Sun at different speeds on different paths, locked in a celestial waltz that repeats but never quite returns to the same configuration. This is the distance problem, and it is the first challenge every mission planner must solve. Earth completes its orbit around the Sun in 365 days, traveling at approximately 67,000 miles per hour. Jupiter, much farther from the Sun, takes nearly 12 Earth years to complete a single orbit, moving at a more leisurely 29,000 miles per hour. Because of this difference in orbital periods, the distance between Earth and Jupiter is never constant. Sometimes the two planets are on the same side of the Sun, relatively close in cosmic terms. Other times, they are on opposite sides, separated by the full width of the solar system. At its closest approach, called opposition, Jupiter is roughly 365 million miles from Earth. At this moment, Earth, the Sun, and Jupiter align in a straight configuration, with Earth positioned between Jupiter and the Sun. This is when Jupiter appears brightest in our night sky, when amateur astronomers can see its cloud bands and even glimpse the shadows of its moons. This is when the distance is at its minimum, when the journey would require the least amount of time and fuel. But the universe does not always grant us this favorable alignment. When Earth and Jupiter are on opposite sides of the Sun, a configuration called conjunction, the distance swells to approximately 601 million miles. This is a difference of over 370 million miles, a gap so vast it could swallow the orbits of Mercury, Venus, and Mars combined. At conjunction, traveling to Jupiter would require nearly twice the distance, twice the time, and exponentially more energy. No mission planner would choose this path, yet it illustrates the profound variability inherent in planetary travel. This variability is not a flaw in our calculations. It is a fundamental characteristic of orbital mechanics. The planets do not move in perfect circles. They travel in ellipses, oval-shaped paths that bring them closer to the Sun at some points and farther away at others. Earth's orbit is nearly circular, its ellipse so subtle that the variation is minimal. Jupiter's orbit, however, is more eccentric. The difference between its closest approach to the Sun, called perihelion, and its farthest point, called aphelion, adds yet another layer of complexity to the distance problem. When Jupiter is at perihelion, it is about 460 million miles from the Sun. At aphelion, it swings out to approximately 507 million miles. This means that even during opposition, the distance between Earth and Jupiter can vary depending on where Jupiter happens to be in its elliptical path. The cosmos offers us not one optimal distance, but a range of possibilities, each requiring different calculations, different trajectories, and different travel times. To make sense of these vast and shifting distances, astronomers use a unit of measurement called the astronomical unit, or AU. 1 AU is defined as the average distance between Earth and the Sun, approximately 93 million miles. This unit allows us to speak about planetary distances in terms that are easier to grasp. Jupiter orbits at an average distance of 5.2 AU from the Sun. At opposition, Jupiter is about 4.2 AU from Earth. At conjunction, that distance stretches to over 6.2 AU. These numbers seem abstract, but they represent the canvas upon which every mission to Jupiter must be painted. The distance problem is not just academic. It shapes every decision mission planners make. Choosing when to launch is perhaps the most critical choice of all. Because Earth and Jupiter are in constant motion, there are only specific windows of time when launching a mission makes sense. These windows occur approximately every 13 months, when the alignment of the planets creates a favorable trajectory. Miss the window, and the mission must wait another year, or risk spending far more fuel traveling a longer, less efficient path. These launch windows are calculated with extraordinary precision. Engineers must account not only for the current positions of Earth and Jupiter, but for where both planets will be months or years in the future when the spacecraft finally arrives. They must predict orbital positions with such accuracy that errors of even a few miles could mean missing Jupiter entirely or arriving at the wrong angle for orbital insertion. The distance problem becomes a problem of time, prediction, and patience. As Earth and Jupiter continue their orbits, their relative positions shift constantly. In real time, the distance between them changes by thousands of miles each day. During the months leading up to opposition, Jupiter draws closer. After opposition, it begins to recede. For mission planners, this fluctuation is both an opportunity and a constraint. Launch too early, and the spacecraft may arrive when Jupiter is farther away than expected. Launch too late, and the window closes, the alignment slips away, and the next opportunity is over a year distant. This is the waiting game, the patience required to explore the outer solar system. Unlike launching a satellite into Earth orbit, which can happen on nearly any clear day, launching a mission to Jupiter requires alignment not just of technology and funding, but of the planets themselves. It is a reminder that space exploration is not just about human ambition. It is about surrendering to the rhythms of the cosmos, about waiting for the universe to present the right moment. The distance problem forces us to think differently about travel. On Earth, distance is static. New York to Los Angeles is always the same number of miles. But in space, distance is dynamic, shaped by motion, gravity, and time. To travel to Jupiter is to navigate not just through space, but through a constantly shifting geometry of orbits. We are not aiming at where Jupiter is, but where it will be, months or years from now, when our spacecraft finally crosses the void and arrives at a planet that has continued its ancient journey around the Sun. This realization is humbling. It reminds us that we are not separate from the solar system. We are part of it, bound by the same forces that govern Jupiter's orbit. Every mission we launch is a conversation with the cosmos, a negotiation between human ingenuity and celestial mechanics. The distance problem is not an obstacle. It is an invitation to think on cosmic scales, to embrace the elegance of orbital motion, and to understand that reaching Jupiter is not just about crossing miles, but about synchronizing with the timeless dance of worlds. As we stand on the threshold of planning a journey to Jupiter, we must accept this truth. The distance is never the same. The journey is never identical. And perhaps that is the beauty of it. Every mission to Jupiter is unique, shaped by the specific alignment of planets at that moment in time. A journey that will never be repeated in exactly the same way. In the vastness of space, even the question of distance becomes a meditation on motion, time, and the eternal clockwork of the heavens. Before we can dream of Jupiter's storms, we must first confront a more earthbound reality. The question is not simply how far Jupiter is, but how fast we can travel to reach it. And here, in the mathematics of motion, we encounter one of the most fundamental limitations of space exploration, a constraint so absolute, it has shaped every mission we have ever sent beyond our world. This is the tyranny of the rocket equation, and it governs everything. Imagine for a moment that space travel were simple. Point your spacecraft toward Jupiter, fire your engines, and accelerate continuously until you arrive. In such a universe, the journey would be measured in weeks, perhaps days. But our universe does not permit such simplicity. Every gram of fuel we carry adds weight. Every kilogram of weight requires more fuel to move it. And that additional fuel itself has mass, which requires even more fuel to carry. This recursive problem, this mathematical spiral, is enshrined in the Tsiolkovsky rocket equation, named after the Russian scientist who first formalized it over a century ago. The equation is elegant in its cruelty. It tells us that the change in velocity we can achieve is limited by the natural logarithm of the mass ratio between a fully fueled rocket and an empty one, multiplied by the exhaust velocity of the propellant. In simpler terms, to go faster, we must carry exponentially more fuel. Double your cargo weight, and you might need 3 times the fuel. Triple it, and you could need 10 times as much. The curve climbs steeply, relentlessly, until the mathematics themselves become an impenetrable wall. This is why spacecraft are fragile, skeletal things. Every instrument, every bolt, every wire is weighed against the cost of carrying it. Engineers do not ask, what do we want to bring? They ask, what can we bear to leave behind? The tyranny of the equation demands sacrifice. For decades, humanity has been bound by the limits of chemical propulsion. When we ignite rocket fuel, whether it is liquid hydrogen and oxygen or hydrazine and nitrogen tetroxide, we are harnessing a controlled explosion. The expanding gases rush out of the engine nozzle at tremendous speed, and by Newton's third law, the spacecraft is pushed in the opposite direction. But there is a ceiling to how fast those gases can move, determined by the chemistry itself. The best chemical rockets can achieve exhaust velocities of around 4 to 5 kilometers per second. This is the speed limit imposed not by engineering, but by the bonds between atoms. And so we have been stuck. Not for lack of ambition, but because the universe itself sets the rules. Chemical rockets brought us to the moon. They launched our probes to Jupiter, Saturn, and beyond. But they did so with agonizing inefficiency, burning vast quantities of fuel to achieve velocities that, on cosmic scales, are painfully slow. Before any spacecraft can even begin its journey to Jupiter, it must first escape Earth's gravitational embrace. This requires reaching what we call escape velocity, approximately 11.2 kilometers per second, or nearly 25,000 miles per hour. At this speed, an object has enough kinetic energy to overcome Earth's gravity and coast into interplanetary space without falling back. It is not that gravity disappears beyond a certain altitude. Gravity's reach is infinite, growing weaker with distance, but never truly vanishing. Escape velocity is the speed at which forward momentum overcomes the infinite sum of gravitational pull stretching outward from Earth. Achieving this velocity is no small feat. It requires enormous rockets, multi-stage designs that shed mass as they climb, burning through tons of fuel every second. The Saturn V rocket, which carried astronauts to the Moon, weighed over 6 million pounds at launch. Of that mass, only a tiny fraction, the Apollo command module, actually reached its destination. Everything else was fuel, and the structure needed to contain it. This is the energy budget of space travel, and it is merciless. Every kilogram matters. A single scientific instrument added to a spacecraft might require hundreds of kilograms of additional fuel to carry it. That fuel adds weight, which requires more fuel, which adds more weight. The equation spirals. Mission planners speak of mass margins and delta V budgets with the precision of accountants, because in space, mass is currency and velocity is wealth. To travel faster, to carry more, to explore longer, all of these ambitions collide with the unyielding mathematics of motion. One might assume then that the solution is simple. Build the biggest rocket possible. Carry the most fuel. Go as fast as we can. But here we encounter a subtlety that transforms the entire problem. Speed, in space travel, is not merely about arrival, it is about stopping. And stopping, it turns out, is just as difficult as starting. This is the deceleration problem, the invisible half of every journey, rarely discussed, but absolutely critical. If a spacecraft accelerates to extreme speeds to shorten travel time, it must also carry enough fuel to decelerate when it arrives. Otherwise, it will simply fly past its destination, a fleeting visitor with no ability to stop and observe. This is why many of our fastest spacecraft, like New Horizons, performed flybys rather than entering orbit. They were built for speed, not for lingering. To enter orbit around Jupiter requires slowing down, firing engines in the opposite direction of travel, bleeding off velocity until the spacecraft's speed matches the gravitational requirements of a stable orbit. This demands fuel, often as much fuel as the initial acceleration required. Suddenly, the mass budget doubles. The rocket equation tightens its grip. Faster becomes harder, not easier. And so mission designers face a profound choice. Do we prioritize speed, accepting that we can only visit briefly? Or do we travel slower, carrying enough fuel to stop, to orbit, to study our destination in depth? The answer depends on the mission's goals, but the trade-off is unavoidable. Speed and capability are locked in an eternal tension. Current spacecraft travel to Jupiter at velocities ranging from about 10 to 20 kilometers per second relative to the Sun, depending on their trajectory and whether they use gravity assists. This might sound fast, and by earthly standards, it is. But in the vast expanse of space, it is a crawl. At these speeds, Jupiter is still months or years away. Light, traveling at 300,000 kilometers per second, reaches Jupiter from Earth in about 35 to 52 minutes, depending on orbital positions. Our spacecraft take 1,000 times longer. Theoretical maximums for chemical propulsion exist, but we are already approaching them. Hydrogen and oxygen, when burned together, produce some of the highest exhaust velocities achievable through chemistry. Incremental improvements are possible: better engine designs, lighter materials, more efficient fuel mixtures, but we are polishing a ceiling, not breaking through it. This is not a failure of imagination. It is a confrontation with physical law. The rocket equation is not a suggestion. It is a boundary, as real as the speed of light. To go faster, to reach Jupiter in weeks instead of months, to send crewed missions instead of robotic probes, we must move beyond chemistry itself. We must find new ways to push against the universe. Some possibilities shimmer on the horizon. Ion drives, which accelerate particles to extraordinary speeds using electric fields, offer higher exhaust velocities but lower thrust. Nuclear propulsion, either through fission or theoretical fusion, could provide energy densities far beyond chemical reactions. Solar sails, propelled by the gentle pressure of sunlight, require no fuel at all, though they accelerate slowly and work best in the inner solar system. Each of these technologies represents a different bargain with physics. Each trades one limitation for another. But all of them acknowledge the same truth. The speed equation is not just about engines or fuel. It is about energy, mass, and the fundamental structure of motion itself. As we contemplate the journey to Jupiter, we carry this knowledge with us. Every spacecraft that has ever made the voyage did so not by conquering the rocket equation, but by negotiating with it. Speed is not a gift. It is earned, calculated, and constrained by mathematics as ancient as the stars themselves. To understand how long it truly takes to reach Jupiter, we must look not at theory, but at history, at the spacecraft that have already made the journey, each carrying within their trajectory a different philosophy, a different purpose, and a different answer to the same ancient question: how do we cross the void? These missions are not just engineering achievements, they are chronicles written in velocity and time, each one teaching us something profound about the art of interplanetary travel. Pioneer 10 arrived in 1973 after 640 days of continuous flight. This was humanity's first emissary to the outer solar system, a spacecraft no larger than a compact car, yet brave enough to venture where no human-made object had ever travelled. Pioneer 10 launched on March 2, 1972, and reached Jupiter on December 3, 1973. Its journey took roughly 21 months, a steady, deliberate crossing that prioritized reliability over speed. Pioneer 10 was a trailblazer in the truest sense. It had to navigate the asteroid belt without maps, without precedent, proving that the journey was even possible. Its instruments were designed to withstand Jupiter's intense radiation belts, something that had never been tested in practice, only imagined in theory. The spacecraft traveled at approximately 32,000 miles per hour relative to the Sun, a speed that seems immense by terrestrial standards, yet translated into nearly 2 years of darkness and distance. What Pioneer 10 taught us was patience, that reaching Jupiter was not a sprint, but an endurance test. Every day of its journey added to humanity's knowledge. Every mile crossed expanded the frontier of what we considered reachable. When it finally swept past Jupiter, capturing the first close-up images of the giant planet, it had already fulfilled its purpose simply by arriving. Voyager 1 made the journey faster, reaching Jupiter in just 546 days. Launching in September 1977, it arrived in March 1979, covering the distance in approximately 18 months. This improvement was not just about raw speed, but about strategy. Voyager 1 benefited from a more direct trajectory and the knowledge gained from Pioneer's crossing. It travelled slightly faster, but more importantly, it travelled smarter. Voyager's success came from understanding that space travel is as much about timing as velocity. By launching during a specific window, when Earth and Jupiter were favourably aligned, the spacecraft minimized the distance it needed to cover. The journey was still measured in years of human time, but compared to Pioneer, it was swift, almost urgent. What made Voyager extraordinary was not just its speed, but what it did upon arrival. It used Jupiter's gravity to accelerate towards Saturn, transforming its mission from a singular objective into a grand tour of the outer planets. In this way, Voyager taught us that every journey to Jupiter can be the beginning of something greater. Galileo, launched in 1989, took a dramatically different path. It did not reach Jupiter until December 1995, a journey spanning 2,242 days, more than 6 years. This seems impossibly slow compared to the missions before it, but Galileo's route was not about speed. It was about precision and scientific ambition. Galileo could not fly directly to Jupiter because the spacecraft was too heavy to be launched with enough velocity. Instead, it took what mission planners call the Vega trajectory, Venus-Earth-Earth gravity assist. The spacecraft first flew inward toward Venus, using that planet's gravity to alter its course, then swung back past Earth not once but twice, each time gaining speed through gravitational assists before finally heading outward to Jupiter. This multi-year detour through the inner solar system seems inefficient, but it was the only way to give Galileo the energy it needed without using prohibitive amounts of fuel. The mission designers were willing to trade time for capability, knowing that once Galileo arrived, it would become the first spacecraft to orbit Jupiter, studying the planet and its moons for years rather than mere hours during a flyby. Galileo's journey teaches us that sometimes the longest path is the most rewarding, that reaching a destination is not always about arriving quickly, but about arriving with the tools and energy needed to truly explore. Cassini faced a similar dilemma. Though its ultimate destination was Saturn, it flew past Jupiter in December 2000 after more than 3 years of travel, using a complex trajectory involving gravity assists from Venus and Earth. Like Galileo, Cassini prioritized scientific capability over speed, carrying instruments so sensitive and comprehensive that the spacecraft weighed more than 12,000 pounds at launch. Cassini's flyby of Jupiter was not its primary mission, but even in passing, it captured stunning images and collected data that revealed new insights into Jupiter's atmosphere and magnetosphere. The spacecraft demonstrated that sometimes a destination can be both a waypoint and a discovery, that even on the way to somewhere else, Jupiter commands attention and rewards those who pause to observe. Then came New Horizons in 2007, shattering all previous records. Launched on January 19, 2006, it reached Jupiter in just 405 days, barely over 13 months. This remains the fastest journey to Jupiter ever achieved by any spacecraft. New Horizons was built for speed from the very beginning, designed not to orbit or linger, but to fly past as quickly as possible, using Jupiter's gravity to accelerate toward its true target, Pluto, lurking in the distant Kuiper belt. New Horizons launched atop the most powerful rocket configuration available, giving it an initial velocity faster than any previous interplanetary mission. It left Earth traveling at approximately 36,000 miles per hour, and it never slowed down. There was no circuitous route through the inner solar system, no patient waiting for optimal alignment. New Horizons was humanity's statement that when necessity demands, we can cross the void with breathtaking swiftness. But this speed came with trade-offs. New Horizons carried fewer instruments than Galileo or Cassini. It could not stop to orbit. It could only observe Jupiter during its brief passage, capturing what data it could in the narrow window of proximity before continuing onward into the outer darkness. The mission taught us that speed is possible, but it requires sacrifice, a willingness to glimpse rather than study, to touch briefly rather than embrace. Most recently, Juno arrived at Jupiter in July 2016, after a journey of 1,796 days, nearly 5 years. Launched in August 2011, Juno took a trajectory that included a deep space maneuver and a gravity assist from Earth in 2013, looping back through the inner solar system before heading outward to its destination. Juno's journey time sits between the extremes of New Horizons' sprint and Galileo's marathon. Mission designers chose efficiency over pure speed, crafting a path that balanced fuel requirements with arrival time, ensuring that Juno would reach Jupiter with enough energy to enter a precise polar orbit, something no previous mission had achieved. Juno teaches us that modern space exploration has become sophisticated enough to optimize for multiple variables simultaneously: time, fuel, orbital requirements, and scientific objectives. The craft's journey was neither the fastest nor the slowest, but it was exactly as long as it needed to be for the mission's specific goals. Together, these missions reveal the art of trajectory planning. There is no single answer to how long it takes to reach Jupiter, because the question itself contains multitudes. Are we measuring the fastest possible journey or the most fuel efficient? Are we planning a flyby or an orbital insertion? Do we have the luxury of gravity assists, or must we fly direct? Each spacecraft that has journeyed to Jupiter has written its own equation, balancing speed against science, efficiency against capability, urgency against thoroughness. The times range from just over a year to more than 6. Yet each duration was correct for its mission. Each journey a testament to human ingenuity in navigating the mathematical poetry of orbital mechanics. As we drift through this historical catalogue of voyages, we understand that reaching Jupiter is not a problem with one solution, but a canvas upon which mission designers paint with gravity, velocity, and time itself. Some missions sprint, others meander. All of them, in their own way, teach us what it means to bridge the impossible distance between worlds. No spacecraft truly visits the outer planets without first considering a celestial dance with gravity itself. We explore how planets become engines, hurling us deeper into the void with no fuel required. A gravity assist is not merely a technique. It is a conversation with the universe, conducted in the silent language of orbital mechanics. As our spacecraft approaches a massive planet, we are entering into an exchange as old as the solar system itself, one where momentum is borrowed, trajectories are transformed, and the impossible becomes achievable. The concept seems almost magical. Approach a planet, swing around it, and emerge traveling faster than when you arrived, all without burning a single drop of fuel. Yet this is not magic. It is physics in its purest, most elegant form. The mechanism is profound in its simplicity. As a spacecraft approaches a planet from behind, relative to the planet's orbit around the Sun, it falls into the planet's gravitational well. The spacecraft accelerates as it is pulled toward the massive body, reaching peak velocity at its closest approach. Then, as it swings around the planet and begins climbing back out of the gravity well, something remarkable happens. Instead of simply returning to its original speed, the spacecraft exits on a different trajectory, carrying with it a fraction of the planet's orbital momentum. To the planet, this exchange is imperceptible, like a moth borrowing speed from a speeding train. But to the spacecraft, it is transformative. Velocities increase by thousands of miles per hour. Journey times that would have taken decades suddenly become feasible within years. Imagine watching this maneuver unfold. The planet looms before you, growing from a distant point of light to a sphere that fills your entire field of vision. Your spacecraft is falling, accelerating under the relentless pull of gravity, yet you are not crashing but curving, threading a precise arc through space. The planet's atmosphere, if it has one, rushes past below. Its moons drift like sentinels watching your passage. Then, at the moment of closest approach, everything changes. The gravitational vector shifts. Your velocity vector rotates. And suddenly, you are being flung outward, slingshot into the darkness beyond, traveling faster than you ever could have achieved with rockets alone. The mathematics governing this maneuver are as beautiful as they are complex. Engineers must calculate the exact approach angle, the precise distance of closest approach, and the optimal exit trajectory. Pass too close, and intense radiation or tidal forces could destroy the spacecraft. Pass too far, and the velocity gain becomes negligible. The target zone is measured in mere miles across a gulf of millions of miles, a threading of the needle performed across interplanetary distances. Timing is absolute. The planets must align not just spatially, but temporally. Miss the window by days, and you may wait years or even decades for the next opportunity. This is why the Voyager missions remain among the most audacious achievements in human history. Launched in 1977, Voyager 1 and Voyager 2 were designed to capitalize on a rare planetary alignment that occurs only once every 176 years. This Grand Tour configuration positioned Jupiter, Saturn, Uranus, and Neptune in such a way that a single spacecraft could visit all four gas giants using a series of gravity assists, each planet accelerating the probe toward the next. Without these assists, reaching Neptune alone would have required over 30 years of travel time. With them, both Voyagers completed their primary missions in just 12 years, visiting worlds that had never been seen up close, revealing moons and rings and atmospheric phenomena that transformed our understanding of the outer solar system. The Voyager trajectory design was a masterpiece of celestial billiards. Each planetary encounter had to be calculated with extraordinary precision, accounting not just for the gravitational pull of the target planet, but also for the subtle influences of distant bodies, the pressure of solar radiation, and even the tiny thrust produced by heat radiating asymmetrically from the spacecraft's nuclear power source. The trajectory team spent years computing and refining the path, using mainframe computers that had less processing power than a modern smartphone. They were choreographing a dance across the solar system, one where every step had to be perfect because there would be no second chances. Yet not all missions to Jupiter employ gravity assists. NASA's New Horizons probe, launched in 2006 toward Pluto, took a different approach entirely. It was designed as the fastest spacecraft ever launched, achieving a velocity that allowed it to reach Jupiter in just over 13 months without requiring a complex series of planetary flybys. New Horizons did perform a gravity assist at Jupiter, but not to reach Jupiter itself. Instead, the Jupiter flyby accelerated the spacecraft even further, shaving years off its journey to Pluto while simultaneously providing an opportunity to study Jupiter's atmosphere, magnetosphere, and moons in unprecedented detail. The Great Red Spot was photographed from new angles. Volcanic plumes on Io were captured erupting into space. All of this was secondary science, bonus observations gathered during a flyby that was primarily about gaining speed. This highlights the cost-benefit analysis at the heart of every mission design. Gravity assists save fuel, which translates to lower launch costs and lighter spacecraft. But they also add time, sometimes years of additional travel, through complex trajectories that wind through the inner solar system before heading outward. The Galileo spacecraft, launched in 1989, took nearly 6 years to reach Jupiter because it used gravity assists from Venus and Earth to gain the necessary velocity. It looped through the inner solar system twice, falling toward the Sun before being flung back outward, each maneuver adding speed but also adding months to the journey. For some missions, this extended timeline is acceptable. For others, especially those with time-sensitive scientific objectives or technological limitations, a direct, fast trajectory may be preferable despite the increased fuel requirements. The decision between fast and assisted trajectories depends on mission, objectives, budget constraints, and the capabilities of available launch vehicles. A heavier spacecraft with extensive instrumentation may require multiple gravity assists simply to reach escape velocity. A lighter probe designed for speed may opt for maximum launch velocity and a direct route. Some missions combine both strategies, using a single gravity assist to trim years off the journey while still maintaining reasonable fuel efficiency. There is no single answer, only a spectrum of possibilities, each tailored to the unique goals of the mission. Looking toward the future, gravity assists will remain essential for deep space exploration. Missions to the outer planets, to the Kuiper Belt, and even to interstellar space will likely employ multiple planetary flybys to achieve the velocities required to reach these distant realms within human lifetimes. Some proposals envision spacecraft that perform a close solar flyby, diving deep into the Sun's gravitational well before being flung outward at tremendous speeds, a maneuver called an Oberth effect that combines thermal shielding with gravitational physics. Others suggest using Jupiter not once, but multiple times, returning periodically to gain additional velocity boosts, slowly building speed across decades until the craft achieves velocities sufficient to reach neighboring star systems within a century. As we consider the journey to Jupiter, we must recognize that gravity assists are more than engineering solutions. They are demonstrations of our ability to work with the universe rather than against it. We do not conquer gravity, we partner with it. We do not force our way to the outer planets. We are invited, guided by the ancient rhythms of orbital mechanics that have governed the solar system since its formation. Every gravity assist is a reminder that the cosmos is not hostile to exploration. It is designed for it, filled with pathways and accelerators waiting to be discovered and utilized. In harnessing the momentum of planets, we become students of the universe itself, learning to navigate not by brute force, but by understanding, precision, and the quiet elegance of celestial motion. As we drift through the contemplation of robotic explorers, gliding silently through the void, a different question begins to surface. One that pulls us from the realm of calculation and into the territory of human fragility. What would it truly mean to send not cameras and sensors, but living, breathing people to Jupiter? The answer is not merely technical. It is biological, psychological, and deeply humbling. A crewed mission to Jupiter is not simply a longer version of a journey to Mars. It is an endeavor so extreme, so unforgiving, that it pushes the boundaries of what the human body and mind can endure. Where robotic spacecraft carry instruments and algorithms, a human crew carries something infinitely more complex: the need to survive. And survival, in the depths of space, demands resources, measured not in kilograms, but in tons. Consider the most basic requirement: water. A single human needs approximately 2 to 3 liters of water per day just for drinking. Add hygiene, food preparation, and the cooling systems that prevent overheating in a sealed spacecraft, and the requirement multiplies exponentially. For a crew of 6 on a mission lasting 6 years, 3 years to Jupiter, time in orbit, and 3 years back, the water requirement alone approaches 40 to 50 tons. Even with the most advanced recycling systems, capable of reclaiming 90% or more of every drop, losses are inevitable. Systems fail, filters degrade, evaporation occurs. Every breath a crew member takes contains moisture that must be captured, purified, and returned to the cycle. The spacecraft becomes not just a vessel, but a closed ecosystem, precariously balanced between life and depletion. Oxygen presents a similar challenge. Each person consumes roughly 800 grams of oxygen daily. Over 6 years, for 6 crew members, that totals more than 10 tons of breathable air. Current technology relies on systems that split water molecules into hydrogen and oxygen, a process that sounds elegant in theory, but demands enormous energy in practice. Solar panels, so effective near Earth, become nearly useless beyond Mars. At Jupiter's distance, sunlight is 25 times weaker than on Earth. Nuclear reactors become not optional, but essential. The spacecraft must carry its own miniature sun, a source of power capable of sustaining life in perpetual twilight. Food is perhaps the most tangible reminder of human vulnerability. Freeze-dried meals, nutrient bars, and fortified supplements can only sustain a crew for so long, before malnutrition begins to erode both body and mind. A multi-year journey demands something closer to self-sufficiency. Hydroponic gardens growing under artificial light, carefully tended crops cycling through harvest after harvest. But plants are not passive cargo. They require water, light, nutrients, carbon dioxide, and constant care. They are vulnerable to disease, pests, and the unpredictable fluctuations of a closed environment. A failed crop is not an inconvenience. It is a crisis. Yet even if we solve the logistics of water, oxygen, and food, we face an invisible enemy far more insidious: radiation. Earth's magnetic field and thick atmosphere shield us from the relentless bombardment of cosmic rays and solar particles. In deep space, there is no such protection. Astronauts traveling to Jupiter would be exposed to radiation levels hundreds of times higher than those experienced on Earth. Over months and years, this exposure accumulates, damaging DNA, increasing cancer risk, and potentially causing cognitive impairment. Shielding helps, but mass is expensive. Every additional ton of water or metal used for radiation protection is weight that cannot be used for fuel, supplies, or structural integrity. And then there is Jupiter itself. The planet's radiation belts are among the most lethal environments in the solar system. Trapped within Jupiter's immense magnetic field, high-energy particles spiral around the planet in vast, invisible storms. Even robotic spacecraft must be hardened against these conditions, their circuits protected by layers of shielding. For humans, spending time in Jupiter's orbit would be akin to standing inside an active nuclear reactor. Brief exposure could deliver a fatal dose of radiation in hours. Long-term presence would be impossible without shielding so massive that it borders on engineering fantasy. Any crewed mission to Jupiter would likely need to maintain a distant orbit, observing from afar, never truly entering the realm where the planet's moons drift in their silent dance. The psychological toll of such a journey is equally daunting, though harder to quantify. 6 years is a significant portion of a human lifetime. It is time spent in a metal capsule no larger than a small house, surrounded by the same faces, the same walls, the same artificial air. Earth becomes a tiny blue dot, then disappears entirely from view. Communication delays stretch from minutes to nearly an hour each way as the distance grows. Conversations with loved ones become exchanges of recorded messages, asynchronous and haunting. A question asked today receives an answer tomorrow. A crisis reported cannot be resolved with real-time guidance. The crew is, in every meaningful sense, alone. History offers glimpses of what prolonged isolation does to the human psyche. Antarctic research stations, submarines, long-duration space missions aboard the International Space Station all reveal patterns: depression, anxiety, interpersonal conflict, the monotony of routine broken only by the occasional emergency. In these environments, small irritations magnify. A crewmate's habit of tapping their fingers becomes unbearable. A disagreement over minor protocol escalates into days of silence. The mind, deprived of novelty and natural stimuli, turns inward, sometimes destructively. Selecting a crew capable of enduring such conditions requires not just technical skill, but profound emotional resilience. And even then, guarantees are impossible. With current technology, a round-trip mission to Jupiter would require at least 6 years, possibly longer. This assumes efficient gravity assists, optimal launch windows, and no major system failures. Compare this to Mars, where a round trip might be completed in 2 to 3 years. Mars is often described as humanity's proving ground, the place where we will learn to live on another world. But Mars is merciful compared to Jupiter. Mars has a thin atmosphere. Jupiter has crushing radiation. Mars receives enough sunlight for solar panels. Jupiter exists in perpetual dusk. Mars is a practice run. Jupiter is the final exam, and we have not yet passed the first course. The technological breakthroughs required for a crewed Jupiter mission are staggering. Closed-loop life support systems must become nearly perfect, recycling every molecule with minimal loss. Radiation shielding must advance beyond current materials, perhaps through electromagnetic fields that deflect particles, or innovative substances that absorb radiation without adding prohibitive mass. Propulsion systems must improve dramatically. Chemical rockets, even with gravity assists, are simply too slow. Nuclear thermal or electric propulsion could cut travel times significantly, but these technologies remain largely experimental, tested only in controlled environments far from the demands of a multi-year deep space mission. And then there is cost. Sending robots to Jupiter is expensive. Missions like Juno cost over $1 billion. A crewed mission would multiply that figure by orders of magnitude. Estimates range from hundreds of billions to over $1 trillion, depending on the mission architecture and level of redundancy required. Such an investment demands not just financial resources, but political will, international cooperation, and a collective belief that the endeavor is worth the risk. In an era where funding for space exploration is perpetually uncertain, securing such commitment is perhaps the greatest challenge of all. Yet despite these brutal realities, the dream persists. Humans have always ventured beyond the edge of the known, driven by curiosity that defies logic and pragmatism. We crossed oceans in wooden ships. We climbed mountains that killed those who came before. We launched ourselves into orbit when failure often meant death. Jupiter represents the next impossible thing, a destination so distant and dangerous that reaching it would redefine what humanity is capable of achieving. To send people to Jupiter is to confront our own limitations and choose to transcend them. It is a journey measured not just in years, but in generations of preparation, innovation, and sacrifice. And perhaps, in confronting the brutal reality of what such a mission demands, we come closer to understanding what it truly means to explore, not as machines recording data, but as fragile, determined beings reaching toward the stars. Beyond the gravity assists and chemical rockets that have carried us thus far, there exists a horizon of possibilities. Technologies not yet perfected, but imagined with such precision that they feel almost inevitable. The journey to Jupiter, measured in years today, could one day be counted in months, perhaps even weeks. To understand how is to peer into laboratories where scientists are bending the rules of physics, harnessing reactions that power stars, and designing engines that consume nothing but light itself. This is not science fiction, speaking to us from distant centuries. This is the threshold we stand upon now, where engineering meets dreams that refuse to remain theoretical. Nuclear thermal propulsion represents the first step beyond our current limitations, where chemical rockets burn fuel and oxidizer to create thrust. Nuclear thermal engines use a reactor to superheat propellant, typically hydrogen, to extreme temperatures before expelling it at tremendous velocity. The efficiency is nearly double that of conventional rockets. What once required vast quantities of chemical propellant could be achieved with half the mass, freeing spacecraft to carry more instruments, more shielding, more provisions for longer journeys. NASA tested nuclear thermal rockets in the 1960s and 70s under Project Nerva, achieving temperatures that would melt most metals, proving the concept was not merely possible, but practical. These engines were shelved not because they failed, but because the political will faded. Today, that will is returning. Modern designs promise specific impulses exceeding 900 seconds, compared to the 450 seconds of the best chemical engines. A spacecraft powered by nuclear thermal propulsion could reach Jupiter in as little as 2 years, cutting travel time nearly in half. The question is no longer if we can build them, but when we will choose to do so. Yet there exists another approach, one that trades raw power for something more subtle and enduring. Ion drives do not roar, they whisper. These engines accelerate ions, typically xenon gas, through electric fields, expelling them at speeds 10 times faster than chemical exhaust. The thrust produced is barely perceptible, no more forceful than the weight of a few sheets of paper resting in your hand. But ion drives can fire continuously for years, accumulating velocity in a patient, relentless acceleration that eventually surpasses any chemical rocket. NASA's Dawn mission demonstrated this beautifully. Launched in 2007, Dawn visited both Vesta and Ceres in the asteroid belt, becoming the first spacecraft to orbit two extraterrestrial bodies. Its ion drive operated for over 48,000 hours, longer than 5.5 years of continuous thrust. The fuel efficiency was extraordinary. The entire mission used less xenon propellant than would fit in a standard car's gas tank. For Jupiter, an ion drive mission would take longer initially, perhaps 3 to 4 years depending on power availability. But it would arrive with far more flexibility, capable of complex orbital maneuvers without the constraint of limited fuel. Ion drives teach us that speed is not always about force. Sometimes it is about persistence. Between these two approaches lies nuclear electric propulsion, or NEP, a concept that combines nuclear power generation with electric thrusters. A small reactor generates electricity, which powers ion drives or Hall effect thrusters at levels far exceeding what solar panels could provide in the dim outer solar system. This marriage of technologies offers a compelling middle ground. The reactor provides continuous, abundant power regardless of distance from the sun, while electric propulsion delivers high efficiency and extended operational lifetimes. Mission concepts suggest that NEP could reduce Jupiter transit times to 18 months or less, while maintaining enough power for active instruments and communication systems throughout the journey. The challenge is not theoretical. It is engineering. Building compact reactors that can survive launch, operate reliably for years in the vacuum of space, and dispose of waste heat effectively requires solving problems at the intersection of multiple disciplines. Yet progress continues. Kilopower reactors, small enough to fit on a table, have been successfully tested, demonstrating that nuclear power in space is no longer a distant aspiration, but an emerging reality. Then there are technologies that abandon fuel entirely, drawing energy from the cosmos itself. Solar sails capture photons from the sun, each particle of light imparting a minuscule push against vast reflective surfaces. The thrust is almost imperceptible, measured in micronewtons, yet it is constant, unending, requiring no propellant, no reactor, no fuel to exhaust. A solar sail accelerates as long as light touches it. For journeys toward the sun, this is extraordinarily effective. But Jupiter lies in the opposite direction, where sunlight grows faint and the pressure of photons weakens. A solar sail bound for Jupiter would need to spiral outward gradually, taking years to build sufficient velocity. Some concepts propose using powerful ground-based or orbital lasers to illuminate the sail long after the sun's light fades, pushing spacecraft to unprecedented speeds. The Breakthrough Starshot initiative envisions laser-pushed light sails reaching a significant fraction of light speed, though their designs target interstellar space, not planetary missions. For Jupiter, solar sails remain more promise than practicality, elegant in theory, but challenged by the physics of diminishing returns at increasing distances. Still, they remind us that propulsion need not always come from within the spacecraft. Sometimes the universe itself can carry us forward. Further beyond lie propulsion concepts that venture into the territory of reactions so energetic they border on the sublime. Fusion propulsion harnesses the same process that powers stars, fusing hydrogen isotopes like deuterium and tritium to release tremendous energy. Unlike fission, which splits atoms, fusion combines them, producing far greater energy per unit of fuel and leaving minimal radioactive waste. A fusion-powered spacecraft could theoretically reach Jupiter in mere months, accelerating continuously at comfortable levels before flipping to decelerate upon arrival. The specific impulse would dwarf anything achievable with chemical or even nuclear thermal systems, potentially exceeding 100,000 seconds. The challenge is ignition. Creating and maintaining fusion reactions requires temperatures exceeding millions of degrees and pressures found only in stellar cores. On Earth, experimental reactors like ITER are inching towards sustained fusion, achieving brief moments where more energy emerges than enters. Translating that achievement into a compact, reliable spacecraft engine remains decades away, perhaps longer. Yet the possibility lingers. If fusion propulsion becomes viable, the outer solar system transforms from a frontier of years into one of seasons. Jupiter becomes a destination we could visit within a human lifetime, not as a singular epic voyage, but as a routine journey. And then there is antimatter, theoretical, exotic, intoxicating in its potential. When matter and antimatter meet, they annihilate completely, converting mass directly into energy with 100% efficiency. No other reaction in physics releases more power. A spacecraft powered by antimatter could theoretically accelerate to half the speed of light, reaching Jupiter in less than an hour. Such speeds collapse the solar system into a neighborhood. But antimatter propulsion remains firmly in the realm of speculation, constrained by challenges so formidable they may take centuries to overcome. Producing antimatter requires particle accelerators and consumes vastly more energy than the antimatter itself releases. Storing it safely, preventing it from touching any ordinary matter, and annihilating prematurely demands magnetic confinement systems of extraordinary precision. Currently, humanity produces antimatter in quantities measured in atoms. A spacecraft would require grams, perhaps kilograms. The gap between laboratory curiosity and operational engine is not a hurdle. It is an abyss. Yet to dismiss antimatter propulsion entirely would be to forget how recently fission, fusion, and even electricity were considered impossible. The universe does not forbid antimatter engines. It simply does not yet offer us the knowledge to build them. So what is realistic? What technologies could genuinely reduce Jupiter travel times within the lifetimes of people alive today? Nuclear thermal propulsion stands ready, awaiting political and financial commitment. Advanced ion drives, paired with nuclear electric power, could launch within the next 2 decades if development accelerates. Together, these systems could bring Jupiter within reach in 12 to 18 months, a transformative reduction from the multi-year journeys of today. Fusion propulsion, if breakthroughs continue, might emerge in the latter half of this century, potentially shrinking transit times to weeks. Beyond that, timelines grow speculative, dependent on discoveries not yet made and physics not yet understood. The technologies that could change the game are not fantasies. They are equations waiting to be solved, reactors waiting to be tested, engines waiting to be built. Each represents a different philosophy of travel, a distinct relationship with energy, time, and distance. Some trade patience for efficiency. Others trade complexity for speed, but all share a common truth. The journey to Jupiter, like all great journeys, is not fixed. It bends to the tools we create and the knowledge we pursue. What takes years today may take months tomorrow, and what seems impossible now may one day be routine. A quiet revolution written not in proclamations, but in the silent trajectories of spacecraft accelerating through the dark, carrying us ever closer to the giants that wait beyond. Out here, speed is easy. Stopping is the hard part. As we race toward Jupiter, the numbers on our navigation screens climb higher and higher, tens of thousands of miles per hour. Faster than any jet, faster than anything we can even feel in a normal human body. Space, after all, is the perfect highway. Almost no friction, no air resistance, no roads to obey. Once a spacecraft is accelerated, it keeps going. No engine hum, no fuel burn, just silent, relentless motion. But motion is only half of the journey. To truly go to Jupiter is not just to reach it. It is to stay, to be captured, to slow down enough that Jupiter's gravity doesn't fling us past into the cold beyond. In spaceflight, this is the stopping problem. There are two kinds of arrivals at a planet, a flyby and an orbital insertion. On paper, the difference sounds simple. A flyby just passes close, takes data, and keeps going. Orbital insertion hits the brakes and falls into a bound path around the planet. But in terms of energy, they are almost different universes. Imagine driving a car toward a city at highway speeds and calling that arriving when you zip through the outskirts without ever turning off the road. That is a flyby, a fleeting glimpse out the window, a momentary handshake with a world. An orbital insertion is like exiting the highway, slowing to city streets, and finally parking. The second step always costs more energy, more time, and more planning. To get into orbit around Jupiter, you have to remove an enormous amount of speed that you spent years building up, falling toward the planet, and gaining momentum from the sun's gravity and Jupiter's own pull. You don't just aim for Jupiter. By the time you arrive, you are plunging toward it. NASA's New Horizons spacecraft is the perfect example of this trade-off. Launched in 2006, it was one of the fastest human-made objects ever sent into space. It reached Jupiter in just 13 months, an astonishingly short time, then continued on toward Pluto and beyond. But New Horizons never stopped at Jupiter. It couldn't. If New Horizons had tried to slow down enough for Jupiter to capture it, it would have needed an enormous rocket stage carried along the entire journey just for braking. That extra fuel would have made the spacecraft heavier. A heavier spacecraft would have been harder to accelerate from Earth. Harder to accelerate means more fuel at launch. More fuel at launch means a bigger rocket. And suddenly, the cost and complexity explode. This is the tyrannical loop of the fuel equation in space. Every pound of fuel you bring to slow down at Jupiter requires more fuel to launch from Earth. That extra launch fuel requires even more fuel to push it. It's a chain reaction of mass. The slower you want to arrive, the bigger and more expensive the mission becomes. So New Horizons made a different choice. It treated Jupiter not as a destination, but as a stepping stone. It dove past the giant planet in a precise arc, stealing a bit of its orbital momentum in a gravity assist, and left Jupiter behind forever. A brief year to arrive, just a few days in its neighborhood, then gone. To truly slow down at Jupiter, missions like Galileo took a very different approach. Launched in 1989, Galileo didn't simply sprint outward in a straight shot. For years, it danced among the inner planets, using multiple gravity assists from Venus and Earth to gradually reshape its trajectory. Each flyby added speed relative to the Sun, but also tuned the direction and timing needed for a gentler approach to Jupiter. Even then, arrival was not a single moment, but a long, careful surrender. For nearly 2 years before reaching Jupiter, Galileo's path was being shaped to make orbital insertion possible. It was as if the spacecraft were learning how to fall correctly, coming in not too fast, not too steep, but along a corridor where a single engine burn could tip it from visitor to resident. On December 7, 1995, as Galileo approached Jupiter, it performed a critical braking maneuver. Hidden behind the bulk of the planet from Earth's view, it fired its main engine for almost an hour. In that silent burn, millions of pounds of chemical energy were converted into lost speed. Just enough lost speed for Jupiter's gravity to seize the spacecraft and bend its path into a looping orbit. In a sense, that engine burn was an act of controlled falling. Instead of slingshotting away to the outer dark, Galileo allowed Jupiter to catch it. But even gravity itself can be used to slow down. We often think of gravitational assist as ways to speed up, to fling spacecraft outward. Yet the same principle can, in theory, be used as a cosmic brake. By approaching a planet or moon from just the right direction, you can give some of your energy back, losing speed relative to the Sun, tightening your orbit instead of widening it. Around Jupiter, its massive moons, Io, Europa, Ganymede and Callisto, become not just places of interest, but tools. By flying past them repeatedly, a spacecraft can reshape its orbit bit by bit, bleeding off speed over months and years. This is gravitational braking, a method Galileo used after arrival to move closer and deeper into Jupiter's system without burning prohibitive amounts of fuel. There is an even more daring idea, using Jupiter's atmosphere itself as a brake. Aerobraking. In theory, a spacecraft could dip into the outermost layers of Jupiter's thick atmosphere, skimming through gas at tens of thousands of miles an hour. For a few minutes, the thin drag would act as a natural brake, converting kinetic energy into heat and slowing the spacecraft without using precious fuel. Then, if everything goes perfectly, it would skip back into space, now traveling slow enough for Jupiter to hold onto it. We have done this at Mars, at Venus, even around Earth. Thin atmospheres can be turned into vast, invisible runways, gently slowing spacecraft over dozens or hundreds of passes. But Jupiter is different. Its atmosphere is deep, violent, and unforgiving. Instead of a soft veil of air, it is a churning ocean of hydrogen and helium, riven by storms the size of worlds. A slight miscalculation in altitude, and the spacecraft would not skim. It would sink, deeper into thicker gas, increasing drag, more heat, more drag, more heat. In moments, the spacecraft could tumble into a death spiral, torn apart and crushed long before it ever reached anything resembling a surface. To dip into Jupiter's atmosphere is to play a razor-edge game with forces that do not forgive. For now, Jupiter aerobraking remains mostly a theoretical whisper, a tantalizing possibility edged with risk. Perhaps future spacecraft, built stronger, smarter, with adaptive heat shields and real-time control, might dare that plunge. But every design must face the same question. How much risk are we willing to take to save fuel? And behind that question lies another, deeper one. What does it even mean to talk about landing on Jupiter? Unlike Mars or the Moon, Jupiter has no solid ground to stand on, no bedrock continent waiting beneath the clouds. As you descend, there is no sharp boundary between sky and surface, just gas becoming thicker, then liquid, then something stranger still. The pressure builds with every mile of descent. The hydrogen around you is squeezed by the weight of entire atmospheres above it. Eventually, the familiar rules break down. Gases compress into exotic forms. In the depths, hydrogen is thought to become metallic, a shimmering, electrically conducting ocean, more like the inside of a star than any sea on Earth. Any spacecraft trying to land on Jupiter would be crushed and melted long before it reached this realm. Atmosphere turns to tomb. Heat and pressure rise beyond the limits of our strongest metals, our most resilient designs. There is no surface to touch without being destroyed in the reaching. We did once dare to dip a toe into this abyss. In 1995, Galileo released a small probe into Jupiter's atmosphere. For about an hour, it fell, sending back data as it plunged through clouds of ammonia and water, feeling winds stronger than any hurricane on Earth. Then, as the pressure climbed to dozens of times Earth's sea level and the temperatures soared, the probe was overwhelmed. It never reached a surface, because in any practical sense, there isn't one. Only deeper and deeper states of matter. So when we ask, how long would it take us to go to Jupiter? We have to decide what go really means. A fast flyby that streaks past in a flash of data and glory. A carefully choreographed orbital insertion that trades years of mission planning for the privilege of lingering in Jupiter's sky. A suicidal plunge into the clouds for a few minutes of information before destruction. Every version has its own clock, its own cost, its own way of answering the stopping problem. Arriving at Jupiter is not like arriving at a city where brakes and roads and gravity are all familiar allies. It is entering the domain of a world that does not offer easy rest. To slow down here is to bargain with physics, with fuel, with time itself. To stay in orbit, to circle those moon worlds of ice and fire, to watch the great red spot roll beneath you again and again. That is not just a question of distance, but of design philosophy. How much patience do we have? How much risk can we accept? How much mass can we launch from one small blue world and send to dance around a giant? As we weigh these choices, another truth begins to emerge. Sometimes, the most difficult part of the journey is not the going. It is deciding how and whether we dare to stop. In space exploration, time is not just something we measure. It is something we spend. Every mission to Jupiter is a decision about how we choose to spend it. Do we sprint past at extraordinary speed, capturing only a fleeting glimpse? Or do we slow down, linger, and let the planet reveal itself layer by layer over years? Between these extremes lies an entire spectrum of possibilities, each with its own philosophy of what a journey should be. At first glance, it might seem obvious. Get there as fast as possible. But in spaceflight, fast is not always better. A higher speed means less time near your target. A quick flyby of Jupiter might last only days in the region of deepest scientific interest. If you are traveling at over 30 kilometers per second, more than 100,000 kilometers per hour, you cross entire planetary diameters in a matter of minutes. Speed, in this sense, is a trade. The faster we go, the more we give up in terms of quiet, patient observation. A mission designed like a sprint is a reconnaissance. A mission designed like a slow walk is a conversation. Flyby missions are the scouts of our solar system. New Horizons, on its way to Pluto, used Jupiter as a pit stop at incredible speed. During its brief encounter, it captured stunning images of storms, auroras, and moons. But it never slowed down. It could not stop to orbit. It simply passed through like a high-speed train rushing through a station, passengers glimpsing the landscape in blurs framed by a window. Yet those blurs are not meaningless. Flybys are often our first introduction to a world. The Voyager missions transformed Jupiter from a bright dot in the sky into a complex system of storms, rings, and active moons. In just a short time near the planet, they collected enough data to fuel decades of research. Fast missions are about coverage, wide, sweeping views, many targets, limited detail. For a restless civilization eager to reach as many worlds as possible, the flyby is tempting. But there is another philosophy, one that values slowness. Orbiter missions commit to a single world the way a ship commits to a harbor. Instead of racing past, they invest enormous energy in braking, shedding speed, so that Jupiter's gravity can gently catch them. This is where the stopping problem becomes real. Every meter per second of velocity, you lose costs, fuel, planning, and time. Yet in return, an orbiter gives you something a flyby never can: intimacy. Galileo, and later Juno, did not just see Jupiter. They lived with it. They watched storms evolve. They traced the delicate structure of magnetic fields over hundreds of orbits. They saw the planet under different lighting conditions, at different longitudes, in different moods. Time in orbit becomes a microscope. What was once a single snapshot becomes a time-lapse of a living world. This is the deep side of mission design. Accepting a longer trip, more complex trajectories, and slower arrivals in exchange for years spent basking in the gravity well of a giant planet. Instead of asking, how quickly can we get there? Orbiters ask, once we arrive, how long can we stay? Beyond even this, there is a more intricate dance, the multi-moon tour. Here, Jupiter is not just a destination. Its moons become stepping stones, each one a gravitational lever used to reshape the spacecraft's path. Rather than spend a huge amount of fuel changing orbits, the mission uses repeated gravity assists from Europa, Ganymede, Callisto, and Io. Tiny slingshots within the larger grip of Jupiter itself. The concept is elegant. A spacecraft dives past one moon, gaining or losing just a bit of energy, adjusting its orbit. Then it arcs to another, repeating the process. Over time, a carefully choreographed sequence of flybys turns into a grand tour of the entire Jovian system. You can lower your orbit, raise it, tilt it, and shift it, all by skimming near these wandering worlds. Each moon becomes both a destination and a tool. This is not fast travel. It is slow, methodical navigation, like tacking across an ocean with the winds and currents, rather than burning engines at full power. But it allows missions to survey multiple moons in detail, returning again and again, catching changes and patterns that a single pass would forever miss. Underneath all these choices is a basic question. Is the mission one way, or is it part of a longer story? Most unmanned probes are one-way travelers. They do not come home. Their design is liberated from the need to carry return fuel or life support. This allows them to be bold with speed and risks. Their round trip is not physical, it is informational. Data flows back along invisible radio waves, crossing the vacuum at light speed to tell us what they have seen. For a robotic mission, time is measured not in crew endurance, but in hardware durability and power. Radioisotope generators slowly fade. Electronics endure radiation until they no longer can. Eventually, every spacecraft becomes silent, left to orbit, drift, or crash into its host world. In that sense, every mission to Jupiter is one way. The craft stays, only the knowledge returns. Human missions, by contrast, would change the calculus completely, forcing us to balance travel time, radiation exposure, supplies, and psychological stress. For now, these remain conceptual, but even our robotic explorers reflect an early version of that thinking. How long can they safely remain? How deeply can they descend into radiation belts? What is the price, in time, of safety? Today, mission designers are beginning to imagine something new, a permanent presence in the Jupiter system. Instead of a single flagship probe that lives and dies with its own limited timeline, imagine a phased approach. Orbiters, landers, atmospheric probes, and eventually relays working together as an enduring network. One mission might focus on mapping radiation environments, another on detailed studies of moons like Europa and Ganymede, another on long-term monitoring of Jupiter's weather. In such a vision, time changes character once again. Jupiter is no longer a destination you visit for a few years. It becomes a place we inhabit, remotely at first, but continuously. A scientific outpost in the outer solar system. Data would flow back not as bursts from single flybys, but as a constant stream, a slow, steady heartbeat of information from a world of storms and ice. Many of these ideas converge in one of our most anticipated missions, Europa Clipper. Europa Clipper embodies a modern compromise between fast and slow, between risk and reward. Instead of going into a low, tight orbit around Europa, where Jupiter's harsh radiation would quickly overwhelm the spacecraft, it will orbit Jupiter itself in a wide, carefully tuned path. From that orbit, it will perform dozens of close flybys of Europa over several years. Each pass will skim just tens of kilometers above the icy surface, collecting high-resolution images, probing the subsurface ocean with radar, tasting the thin atmosphere and any water plumes that may erupt into space. Then the spacecraft will retreat back into a safer, more distant orbit before diving in again. Approach, observe, retreat, repeat. This strategy is a masterpiece of trajectory optimization. It accepts that Jupiter is dangerous and uses that danger as part of the design. Timing is everything. Each Europa flyby must occur at just the right moment, at just the right angle, to gather maximum data while also setting up the next orbit, the next dive, the next encounter. Europa Clipper will not race through the Jovian system. It will thread it. Its journey to Jupiter will take years. Its orbits will be meticulously calculated to balance science, safety, and time. It will not land. It will not stay in one place. But by returning to Europa again and again, it will build something far more profound than a single snapshot, a narrative, a story of an ocean world that might, in the darkness beneath its ice, harbour conditions suitable for life. Fast missions show us where to look. Slow missions show us how to understand. Multi-moon tours teach us how to navigate not just space, but gravity itself. One-way probes turn years of silent travel into moments of revelation. Future networks may one day transform Jupiter from a far-off giant into a familiar neighbour. In the end, mission design to Jupiter is not just an engineering problem. It is a philosophical one. How much time are we willing to invest in wonder? How patient are we prepared to be with a world that moves on cycles measured in centuries, storms, and epochs? Between fast and slow lies a simple truth. The universe is not in a hurry. And when we choose how to go to Jupiter, we are really choosing how we wish to experience time itself. So after all this distance, all this math, all these slingshots and storm watching, how long does it really take to go to Jupiter? In one sense, the answer is simple. In another, it refuses to be pinned down, like a storm that never stops moving. If we look at the history written in metal and trajectory plots, we find a clear range. Robotic spacecraft have taken anywhere from about 13 months to nearly 6 years to reach Jupiter. New Horizons, launched like a cosmic bullet, raced there in just over a year. Galileo and Juno, more patient travelers, spent years looping through the inner solar system, borrowing speed from Venus and Earth, before finally surrendering to Jupiter's pull. On paper, the numbers seem straightforward. In reality, each number hides an entire philosophy of travel. If we ask what is possible with near-term technology, rockets and propulsion systems that are extensions of what we already know, then the fastest practical journeys are under 2 years, using a direct, high-energy trajectory. No looping gravity dances, no elaborate planetary tour. Just a hard burn from Earth, a steep path outward, and a long committed fall toward the giant. Such a mission would be unforgiving. It would demand tremendous energy at launch and equally careful braking on arrival if we wanted to slow down and stay. The spacecraft would endure intense radiation, high speeds, and limited chances to course correct. It would be a sprint across a cosmic marathon track. Faster is possible in theory, of course. If we push the boundaries into advanced propulsion, technologies still under development or existing mostly on drawing boards, the trip time begins to compress. Ion engines running continuously, nuclear thermal rockets heating hydrogen to searing temperatures, or even more exotic concepts like nuclear electric propulsion and fusion-driven designs suggest a different kind of voyage, one where we don't just fall toward Jupiter, we accelerate to it. In those imagined futures, Jupiter shifts from a distant, once-in-a-decade opportunity to something almost visitable. Trip times could shrink to months. In ambitious scenarios, perhaps even weeks. Not overnight, not instant, but fast enough that the gap between human lives and planetary distances begins to narrow. Yet those are still, for now, whispers of what might be. Engines we are testing, concepts we are refining, stories we are not quite ready to tell in metal and fuel. When we ask how long it would take us, human beings, fragile and biological, to go to Jupiter, the clock rewinds into caution. A human mission is not a single number of months. It is food, water, air, radiation shielding. It is medical systems, redundancy, backups for the backups. It is the reality that people cannot simply be pointed at Jupiter and left to drift. They must survive the journey, the arrival, and the return. If we imagine a crewed expedition, not just flying past, but arriving, studying, exploring its system of moons, then curving back home, the timeline stretches. Even with aggressive trajectories and advanced but plausible propulsion, a round trip would likely be measured not in months, but in years. 3 to 6 years is a reasonable envelope. A mission architecture that might launch in a fast window, fall toward Jupiter, spend time in orbit or in the Jovian system, and then ride another carefully planned trajectory back to Earth. Any slower, and the risks compound. Any faster, and the engineering pushes harder against what we can safely do with human bodies in deep space. And still, the question resists a single answer. How long does it take to go to Jupiter? It depends, deeply and irreversibly, on why you are going. If your goal is a quick scientific flyby to snap images, gather data, and continue into the dark, you aim for speed. You shave months from the journey, accept higher energy demands, and never slow down enough to stay. In that story, Jupiter is a gate, not a home. If your goal is to orbit, to linger in the embrace of its gravity, to map its moons and sample its radiation belts, you choose patience. You trade a fast arrival for a survivable one, using gravity assists and long arcs that stretch the mission to many years. Jupiter becomes not just a waypoint, but a laboratory. If your goal is human exploration, the definition of how long it takes intertwines with human endurance. We must ask, how long can we keep people alive, healthy, and sane within a small, sealed world, drifting far from any rescue? The answer is not measured by rocket thrust alone, but by psychology, medicine, closed-loop life support, and the delicate ecosystem we must rebuild inside a spacecraft. There is another layer, quieter, but just as important, the philosophical one. Is Jupiter even a realistic destination for us, as human beings? Not in the way Mars is. There are no landing pads waiting on Jupiter, no solid ground where boots can press dust into memory. Jupiter is not a place to stand. It is a pressure gradient, an ocean of gas and liquid and metallic hydrogen, where the concepts of surface and sky blur into something alien. Its radiation belts would tear through unprotected human tissue. Its storms would dwarf any structure we could build. If humans ever go to Jupiter, what we truly mean is that they would go to its realm, to orbit, to its moons, to the icy shell of Europa, or the mysterious depths of Ganymede's buried ocean. The true destinations for human explorers are almost certainly the worlds that circle Jupiter, not Jupiter itself. In that sense, asking how long it takes to go to Jupiter is like asking how long it takes to reach a mountain range you can never climb, but whose valleys and foothills may someday hold your home. Jupiter is a beacon, not a landing site, and yet that beacon matters, because traveling to Jupiter, whether with a robot or one day a crew, is not just about reaching a single planet. It is a test of our ability to cross the threshold into the outer solar system. Everything we learn about going to Jupiter becomes a key for unlocking the worlds beyond. The trajectory designs that brought Galileo and Juno to Jupiter are the same ones that send voyagers and new horizons far past Neptune. The radiation shielding that protects a spacecraft near Jupiter teaches us how to protect instruments, and eventually people, around other giant planets. The life support and propulsion that might someday sustain a crewed mission to the Jovian system are the same technologies that would carry us onward to Saturn, Uranus, Neptune, and perhaps even the dark interstellar sea beyond. So when we ask, how long does it take to go to Jupiter? We are also asking a bigger question. How long does it take before the outer solar system is within reach of our species? In the age of chemical rockets and gravity assists, Jupiter lies at the edge of our patience, a destination of years. In an age of advanced propulsion, it may contract into months. In some far future, with technologies we barely dare outline, these distances might be as ordinary as crossing an ocean was to our ancestors. For now, the answer is layered. For a fast robotic mission with today's technology, about 13 to 24 months. For methodical orbiters and complex scientific payloads, 3 to 6 years, sometimes more. For future advanced drives, perhaps months in the boundary where engineering and imagination begin to overlap. For humans, with everything that implies, a round trip likely lasting 3 to 6 years at minimum, an entire chapter of a life devoted to a single journey. There is no one number because there is no one Jupiter. There is Jupiter the flyby, Jupiter the orbit, Jupiter the slingshot, Jupiter the training, ground for interstellar dreams. Every mission chooses its own answer. In the end, the time it takes is not just the span between launch and arrival. It is the centuries of curiosity, the decades of engineering, the years of planning, and the months of quiet coasting through darkness in between. It is the long arc from the first time someone looked up and saw a bright, wandering star in the night sky and wondered what it was, to the moment a human-made machine first fell into its gravity and watched the great red spot roll beneath its gaze. So, how long does it really take to go to Jupiter? As long as it takes to decide what we are willing to risk, what we hope to learn, and how far we are ready to let our journeys reshape us. The clocks will keep ticking. The orbits will keep turning. Jupiter will wait, massive, patient, unhurried. And somewhere, in the spaces between seconds and centuries, we will decide what going to Jupiter truly means. We began with a simple, restless question. How long would it really take to go to Jupiter? A question you might whisper to yourself in the dark, staring at the ceiling, wondering how far really is. Along the way, that question unraveled into something much bigger. Distances that change with every orbit. Speeds that depend on engines, fuel, and patience. Gravity assists that turn planets into partners. And timelines that stretch not in days or weeks, but in years, sometimes in decades. What started as a countdown became a story. We discovered that there is no single answer, no neat number you can write on a sticky note. A fast probe might race to Jupiter in just over a year. A careful, crude mission might take far longer, slowed by the needs of fragile human bodies and the demands of safety. Advanced propulsion could someday shorten that journey dramatically, but even then, space will always ask for something we cannot rush: patience. Deep space exploration is not just about technology, it is about temperament. Every mission to Jupiter, real or imagined, is an agreement with time. Engineers spend years planning trajectories that unfold over another set of years. Spacecraft coast in the darkness while the people who built them grow older back on Earth. Children who saw a rocket launch may be adults by the time the first images arrive from the outer planets. In that sense, a journey to Jupiter is never just a voyage across space. It is a voyage across human lives. And yet, we keep going, because Jupiter is more than a destination. It is a mirror that reflects our curiosity back at us. Its storms, its swirling bands, its icy moons hide in oceans in the dark. All of it reminds us that the universe is not a finished picture, but a work in progress, still full of questions we have not yet learned how to ask. When we send a spacecraft into the deep beyond, we are really sending a question. What else is possible? Right now, as you listen, probes are gliding through space, silent and tireless, obeying the same gravitational rhythms that guided Voyager, Galileo, and Juno. Someday, perhaps, a crewed ship will follow, carrying human eyes that can watch storms rise over Jupiter's horizon in real time. Whether that happens in your lifetime, your children's, or your grandchildren's, the direction is clear. Humanity's reach is slowly, steadily, extending outward. Jupiter is waiting. It does not hurry. It does not complain. It simply turns, wrapped in clouds and lightning, patient in a way only a planet can be. Before you drift off to sleep, imagine this. Somewhere in the future, a person stands at a spacecraft window, looking down at the great red spot, knowing that generations of dreamers wondered what that exact moment would feel like. The years it took to get there, the calculations, the careful burns, the long coasts through the dark, all of it collapsing into a single breath of awe. If this journey through space and time kept you company tonight, you can gently tap like to help others find it too. Let me know in the comments where you're listening from. A city, a small town, a dorm room, a night shift, anywhere on this tiny world circling our modest star. I read those places like stars on a map, tiny lights scattered across Earth. If you'd like to explore more of the cosmos together, you can subscribe and make these trips a regular part of your nights. And if you want to go one step further, YouTube membership is there as an optional way to support the channel. Never required, always appreciated, like an extra booster stage on our shared journey. For now, let the numbers fade. Let the years and miles blur into a gentle, distant glow. Out beyond Mars, past the asteroid belt, through the realm of giants, Jupiter turns slowly in the dark. Whether it takes us 1 year, 10 years, or an entire generation to stand in its shadow, it will be there, waiting. Close your eyes. Breathe. Somewhere, far beyond the clouds, your questions are already on their way. Sweet dreams among the stars. Jupiter awaits.